There we are. Welcome everybody to the September 2021 meeting of the Howard Astronomical League. I want to let everybody know that this meeting is being recorded and it'll be available for playback after the meeting and probably for the next month or so for anybody who wants to catch up on something you may have missed, or for those who are not on the call who have asked me to record it for everybody. So welcome. For those of you who may not know me, my name is Phil Whitebloom. I'm the president of HAL, and I'm thrilled to have everybody here as usual. We have some great, a lot of great topics for tonight. And so I'm going to move through the business stuff pretty quickly. But one of the most important things is the next slide. And it's in honor of our guest speaker tonight. So here we go. Wrong slide. There we go. There you go.
I love it. I want that. I'm going to start using it.
All right. I'm going to send it over to you afterwards. No, there you go. All right. So first, I want to welcome any new members that are on the at this meeting today, or any guests. So let me just open it up. Is there any new members on today? Just unmute yourself and say hello.
Hello, my name's Crystal Rowland. I'm actually a teacher at Glenelg Country School. We just had our observatory restored, so
Right.
I'm hoping to get to know you guys' club.
Well, welcome.
Welcome.
Glad to have you.
Welcome. You
We
mean
get to out at Glenelg one day. It's been a long time since we've been out there. So, who else? Any other new members?
Hi, I'm a new member. My name is Rachel, and I just really like the stars and astronomy, and I wanted to get my kids into it.
All right. Well, we're thrilled to have you. Have you made any of our events yet? Either one of you, Crystal or Rachel?
I came to the one on the, September 11th.
Okay.
No, I just found out about this yesterday, so.
Okay, so we'll forgive you for missing September 11th. Any other members, new members? Any guests, first-time guests, besides our guest speaker, Danny?
First-time guest.
Hello, Karina. Welcome.
Hello.
Welcome. Anybody
Hi,
else?
Karina. Hi, Karina.
Hi.
One of Michelle's.
I invited her.
Okay, we bill Michelle directly for guests, so whether she invited them or not, just so you know. Well, let's give everybody a good Zoom welcome for our new members, our guests. So I want, so what I need is, if I could ask somebody, Jim, Wayne, or somebody, or Yvonne, to watch the chat when we get going, because I have a hard time managing all this different stuff. And if there's question or comment in the chat they want to share, just open up the mic and interrupt, and that would be great. What I want to let everybody know is, for the last few years, and maybe a little before, I've been the most visible person to everybody, but I'm not the person doing all the work for sure. We all benefit from the work of all these people here and other volunteers that are not on this list. So I want to make sure that we give a special call out to all of our officers and committee chair people who really make this club work so well. And as I was saying before some of you joined, that we're well over 300, about 320 some members, over 260 families. That's just awesome. And especially, what's going on. So I want to just kind of reach out to anybody, all of our officers here, and give them some recognition. So thank you guys and ladies. Do any of the officers have anything you want to report today to the group?
No, this is Victor. I would just say that the feeling is mutual, and thank you, Phil, for doing everything that you do for the club.
You're welcome. It's my pleasure. I enjoy this as much as, if not more than anything else. So I always like to say above and below the clouds, because one of the things that we specialize is how to keep everybody interested in astronomy when we're clouded out the majority of the year for so many of our events. And we still have lots of people who show up. And but I have to tell you that except our public meeting that I think Rachel mentioned on September 11th was the first successful public meeting star party that we've had since probably the fall of 2019. We had a couple years of rain. We were stopped from doing public events because of COVID. All the ones that we started this summer were clouded out or rained out or both. And but we had clear skies. We had over 30 telescopes show up. And what was really interesting about that is that there were people who brought their telescopes out that were not members of this club. There were visitors that heard about it. And I was so pleasantly surprised when I go up and talk to some people and catch their names and, and find out that they just heard about the meeting and they came out, they brought their telescope and set up and we're letting other people share in. So I don't remember that happening too much in the past. So that was great. And plus we had over between 150 and 200 visitors at the event that night. And so we started at sundown and ended at 11 o'clock officially. The members stayed quite late that night because it was clear. So it was really, really a very successful event. So thanks to everybody who came out with your telescopes and worked with the public, and we know we got a lot of new members as a result of that meeting too. And David, I'm loving your haircut, by the way, just so you know. But this Sunday we have a big event. The Robinson Nature Center is having their open house again, their first one since COVID. And we always participate on the green roof. And I saw a couple more emails come in just before I launch this call. So I'll get back to those of you who sent me some saying you're going to come and participate with your scopes or just come out. But tonight, right now, it looks like we have 9 or 10 solar telescopes ready to go for this event. And it's supposed to be beautiful weather. So it's going to be awesome. So remember I sent out to those who are coming out with telescopes, I sent out the specifics on when to arrive, how to drop off your equipment and where to park over at APL, and they'll shuttle bus you back. But it's really important that we're set up at 11:45 and there's going to be a lot of people there. I'll be setting up about 10. I'll show up about 10 and get everything organized for us. So this is going to be a great event again. So here's what we have coming up for our next members only is October 2nd. And then October 16th is our next public meeting, star party. And October 16th is also the International Observe the Moon Night, which Joel is coordinating. I know Michelle and Hannah and others will be helping out. We'll have some tables set up. We'll probably start early when it's still light times, light outside. And I won't be there, unfortunately. I'll be out of town visiting one of my children, but you guys will have a great time, and I'm sorry we're gonna miss it, but it's in great hands with all of you. So that ought to be a wonderful time, and hopefully the weather will cooperate. What's coming up as far as in the sky? Here you could just take a quick look. I'm gonna, I'll get this over to our webmasters there, and they could post this too, so you can see it. But if you jot down that email address there, or the website address rather, that's where this information is, as well as other places. But you can see there are a few things happening in October, celestial events. So that's kind of a subset. And moving right along, that's all the business I have. Does anybody have any general questions before I introduce our first presenter before we get to Danny? No? Okay. So, no, go ahead, Daniel.
Do you know when we're going to start having the in-person HAL meeting at the Robinson Nature Center again? Do you know when that's going to start up again?
So we're still in discussion, but what's probably going to happen is we're going to continue to do the monthly meeting like we're in right now on Zoom, because we have so many more people that could make it. And I don't have to mess with the technology of doing it in person or anything else. So what we're going to probably do is we're going to use the Robinson Nature Center for in-person meetings, for astro schools, for just get-togethers, and they won't be on Zoom. They're just going to be in person, and it'll be an additional monthly event. So that's going to start pretty soon.
That'll be at the Nature Center, but still have the monthly HAL meeting on Zoom.
Yeah, that's the plan right now.
Yeah, it seems like it's gonna, to me, it could go on forever.
Well, we don't want COVID to go on forever, but we want the HAL to go on forever. So
Hopefully, when it's over, then we'll be back to normal. It's the Robinson Nature
hopefully
Center.
so. Hopefully so.
Thank-
Thanks for the
thank you.
question, Daniel. Go ahead and make sure you mute yourself again, okay, please? So Don Nab with the Mideast Regional Astronomical League, he's in charge of that, and he's been doing a wonderful job. We've had so much communications from Merrill, more than ever before because of Don's efforts. And once again, Don, congratulations on the award you received recently.
Thanks.
Yeah, and Don's gonna just go over some slides. He's gonna tell me to prompt me through them, and he's gonna tell you about the Hunter program. So Don, I'll give it to you.
Okay, well, this really comes out of a conversation that Phil and I, and there was someone else in your club involved, your Alcor maybe?
Steve is our
Right, Steve, and
our Alcor.
we talked in the summer about, how do we all the clubs, your clubs that I can think record members, right? Record number.
Yeah, for
And the
sure.
club I'm in is at a record number. My main club, I'm in the second club, is at a record number of members. All these new members, we want to make sure they know what the Astronomical League is, what the Mideast region is, and also come up with something we could do as a region together, all the clubs. So really, this idea goes back, I rather thank Phil for it. He's the one that planted the seed and got me started on this. So just a few slides, something we can do to educate new members and get them involved in visual astronomy and amateur astronomy. So the league, all of you are a member of the league, and we may not know it, but all of you are members of the Mideast region of the league. So, the league's 300 clubs. It's at a record 21,000 members. That slide, the image on the left there, that's the league website. Just so you know, the website is in not great shape. It's going through some renovation and will probably next year be moved over to an entirely new platform, but it still has a lot of good stuff. The regions are on the right. There are 10 regions. We are that yellow one on the right. So, okay, you can advance it, Phil.
Okay.
And so I didn't know what Merrill was until a couple of years ago, but Merrill is the Mideast region of the Astronomical League. That's us. So that lower left image is the current website on the Astronomical League website. It's out of date. They can't even update this thing. Terry Trees there. He was chairman 2 years ago. I've replaced him. Al Lamperti is still our regional representative. So hopefully when this website is updated, they're going to make this a little bit more modern, but it's about 40 clubs in the area. And almost everyone, including all of you, I think, are members of the league, and you can participate in what they call observing programs. There's 60 of them. There's all kinds of different things. You can look at the moon. There's 2 levels of looking at the moon. There's the Messier objects. There's double stars, there's binocular special ones, there's naked eye ones. But we decided to pick out one to work on as a region. So you can advance the next one. And we decided to go for the Constellation Hunter program. It's a great, fun program. So many new members in all the clubs. It's a great way to learn the night sky. Our club teaches astronomy classes in the spring. I always tell, it's for beginners. I always tell them the 3 most important things about observing is 1, to learn the sky, 2, to learn the sky, and 3, to learn the sky. Nothing that will give you better enjoyment and better development of your skills than learning the night sky. So we would work on the northern skies, and it's to provide an orientation to the sky for novice astronomers, or it may be experienced one that doesn't know all the constellations. Okay, so you can go on.
Oh, hang on a second, that's stuff.
Yeah. And a great thing about this is you don't need a fancy telescope. It'd be nice to have binoculars, but you don't need binoculars. You don't need anything special other than a sky chart and a reference for the brighter stars. Probably good to have a red light so that because you're going to have to sketch these constellations, it'll allow you to be able to see the paper in front of you. But it's a forum for a novice observer to learn the constellations, to learn to navigate among the stars, and then once you know the constellations, then you can go on to other programs, all the other 60 that are there. So it's a good start for everything.
Hey, Yvonne?
Yeah.
Yvonne?
Yes,
You started this program, right?
I did. And
There's
I
another thing
printed-
that people should remember to bring, right?
Yes, they are. Yes. And
Yeah,
I,
like a blanket or something to keep yourself warm when you're out in the dew. In the
yeah,
wet.
you do get chilly. And I was thinking a blanket would be good to put in the car for my legs. I had layers for the top, but my legs didn't have layers.
Yeah. So yeah, Don,
I'm really glad
was
that
out-
you're doing this presentation.
Yeah, Yvonne was out with us the other night. She started this program ahead of time.
Good. That's great to know. Okay, so first thing you start with is to download a star map. And actually, there's another one available, one called What's Out Tonight. It's also a website that has a very nice star map. Every month, you can download this and print this for free. It's a great start to look for the constellations. And I recommend binoculars because I'm not sure about your area, but where I live, it's kind of light polluted and you can see some of the fainter stars, but you only sketch the things that are the major stars. You don't try to make an artist's impression of the entire sky, just and you'll see an example in a slide or two from here, but binoculars can be a big help. Okay. So full information is at the Astronomical League website. This is a slide capture, a screen capture from the actual observing program page on the website. Okay, and it's got all the rules and all the things you need for it.
Right.
Okay.
Everybody
Next.
knows that Steve Jaworski, wave Steve, so we could see you. There he is. So he's our ALCOR, he's our Astronomical League coordinator. He's also a multiple pin recipient for doing many programs from the Astronomical League. And he, if there's any specific questions, you could reach directly out to Steve and he could answer them and or we could go out to Don. There you go. Back to you, Don.
Okay, you can go to the next slide. So what do you need to do? You observe and sketch all the constellations in the northern sky. Now, on the right, you can see you don't have to be an artist to be able to do this. I am not an artist. Neatness doesn't count. All right. So, but that's all you have to do. And this file, a file of this PDF or an Excel file is available. I'd send it out to Phil, but also there'll be a link that Phil will share with you to go to the Mideast region website, and you can download this file either in Excel form or PDF form. You can get one also from the Astronomical League site, but I think this is a better form. You'll see the two side by side, but clearly you don't have to be an artist. It's just if you can draw a stick person, you can do this program. Okay, next. Yeah, obviously you don't need to be an artist, that's for sure, okay? And now it can take you up to a year to do this because all the constellations aren't always in the night sky at the same time. Here are the two forms. The one on the left you can get from the AL website, but the one on the right I designed, you can get it from the either from Phil or you can, if he gives you the link, you can get to the Mideast region website and download it from there.
Yeah,
I put a whole page of resources for this.
I'll send everybody out sometime this weekend, this information, and then we'll find a place to post it on the HAL website.
Yeah, I built a whole, just today, I built a whole new page on the Mideast region website that has all the resources you need to do this program, to make it all in one spot.
Yeah, I'll put that link in there and that'll be easy. Okay.
Okay, all right. Next. So at 39 constellations, this is a list that you also get from the Astronomical League website. Okay. And when you're done, this is what you get: a beautiful pin to wear or to put on your purse or your briefcase. You get a certificate. You probably can't see it, but that's mine from 2009. It was one of the first programs I did when I joined our astronomy club. And you get your name in the reflector on the observing awards. So it'd be great, almost a year from now to see a whole bunch of names from the Mideast region showing up on the Northern Constellation Hunter program. It would be wonderful. So it's a fun program. I think you'll enjoy it, especially if you have a couple of folks doing it together. It can be really fun. Any questions?
All right.
This is Yvonne. I have a question.
Huh?
So in a way, I started it. I had downloaded the sheets from a few months ago. You had mentioned it, Don, and I started checking things off, but I did not realize I was supposed to be sketching. So now I have some catch-up homework to do, and I'm looking forward to accessing the sheets. So I'm glad that you're talking about this. Thanks.
Okay. Yeah. This is now the third club I presented this to. So hopefully get some some inertia going and get people moving toward it. So it's fun.
So thanks,
I
Don.
also,
Mhm.
Anybody else?
yeah, I have a question.
Go ahead.
Okay, so is there any time frame in which you have to complete the activity?
It could take you a couple years if you want to. I have some programs. I'm working on the Lunar 2 for like the last 5 years. So there is no limit on the time.
Okay, I'll try submitting it when I'm 13.
Thanks. All right. So, hey, just so you know, my computer has locked up a couple of times during these meetings and stuff. So if I should drop off, we've learned that the meeting stays together. It doesn't go away. So if somebody else just pick it up and keep on going, and I'll be back on. This is my computer reboots. But so thank you very much, Don. We really appreciate it. And
thanks for
you're
having me.
welcome to any of the meetings with any information and or just to participate. So and we will send you some pictures from the club too. We haven't started doing that yet.
Right, thanks.
All right. So next month, before we get to Danny here, our guest speaker is going to be Dr. Kerry Leese. I don't know exactly how to pronounce his last name there, but he's going to be speaking to us about the New Horizons mission and the Kuiper Belt. So should be another outstanding presentation. But now it's time for our main event tonight, Danny. And no matter how much I'm going to practice, I'm going to mess his name up. So I'm going to call him Dr. Danny. Dr. Danny Milisavljevic. He'll say it when he gets on. So I don't want to embarrass myself or him. But we're thrilled to have you with us today. Let me give you a quick introduction. Dr. Danny is an assistant professor in the Department of Physics and Astronomy at Purdue University. He completed his undergraduate degree in liberal arts at McMaster University, master's degree in philosophy at the London School of Economics under a Commonwealth Fellowship, and PhD in physics and astronomy at Dartmouth College. He held research positions at Harvard University and the Smithsonian Astrophysical Observatory. Dan's research interest includes multi-messenger signals of astrophysical transients discovered via time domain surveys, autonomous AI directed coordination of global observing facilities, the explosion mechanisms, progenitor stars, and compact object remnants of supernova, massive star mass loss, and the formation and destruction of dust and molecules. Something I'm sure it's a great party topic, I'm sure. And with that said, I'm going to unshare my screen, Danny. And so you could share yours. You should be able to, we didn't try ahead of time, but you should be able to pop yours up.
Yes.
And welcome, and we're thrilled to have you. And would you take questions during your presentation, or do you want to wait till the end?
Absolutely. Please, typically there's a moderator. Phil, maybe you play that role. So if somebody puts something in the chat, you can act on it.
Yeah.
I also won't be offended if somebody tries to speak up as I am.
Okay. And before you start, just so everybody knows, after the presentation, Chuck Cinnamon. Chuck, are you on? Hopefully he's there. Chuck's got a little thing that he does that kind of feeds off of what Danny's going to talk about, and then we're going to go into quite a few astro images that all of you have sent in.
I'm here, Phil. Just
Okay, great, Chuck. All right, Danny, it's all yours.
All right, Phil, thank you for the wonderful introduction. Yeah, I know my name is a mouthful. Milisavljevic. That's level 1. Level 2 is Milisavljevic, when you put the accent on the J. Anyhow, it's delightful to get an invite to speak to the Howard Astronomical League. Today, I'm going to give you an insight to what I think is one of the most important phenomena in the universe. And as citizens here of the universe, we should know something that's been critical for our existence. And I'm going to talk about the history of observing supernova explosions and our preparations for the next nearby event that's going to happen in our own backyard, Milky Way. So to start off, just so you're aware, I'm not presenting work that's my own. I work with a super elite group of students and postdocs at Purdue University. At heart, we are uber nerds, but we try to look cool in group photos like this. So this is from a couple of years ago, and we usually have some movie theme. Here is, in times of COVID, when we started having to do Zoom calls, the dog Wilbur, who's actually just getting out of his basket now for a stretch, is the team mascot. Of course, it's themed after the Brady Bunch. And here is the latest photo taken around May. And it was interesting. I coined this. I wanted to do the movie Contact, and the younger generation of undergrads weren't so familiar with it. So I found that as a part of their academic experience that we had to watch the movie Contact. Okay, so what I want to impress upon you is that we have watched stars explode. Okay, so in astronomy, we talk about stars, we view stars all the time. We've actually watched stars explode. So here's among the most dramatic examples. This is a star in the Large Magellanic Cloud, Sanduliac -69202. Now, if there wasn't an arrow there, it wouldn't be anything out of the ordinary. You can see there are other stars of comparable brightness, and there are even brighter stars to the upper left here. But in February of 1987, this happened. There was a supernova, 1987A, A being the first supernova of 1987. It's also appropriate that was co-discovered by a Canadian. 1987, A. I can use that joke because I'm Canadian, or you roll your eyes if you don't think it's so funny. Anyhow, look at this. So it started off as a star and it exploded. And if we go back years later with the razor sharp vision of the Hubble Space Telescope, and here it is floating over here, we can see that, and we do a nose count, the star is no longer there. Now, I could do actually a whole presentation just interpreting this image alone. This ring and this ring is not from the supernova. That's left behind by the progenitor system, the star or stars that were there beforehand. This ring as well is not associated with the explosion. That's also the progenitor system. They think this was ejected about 20,000 years, 10 to 20,000 years before the star exploded. This stuff in here is the actual stellar debris. We're going to see a lot of that in the upcoming slides. Okay, so the star is no longer there. It truly was a terminal explosion. And in the time that I was waiting to start, Arjun said he was wanting to image the Tarantula Nebula. So I grabbed this image. Here's the Tarantula Nebula, and here's actually 87A as it was one of its brightest points right here. So it's faded since I showed you the image years later. It's no longer visible like this, but at some point it became naked eye visible, and that's how it was actually discovered from Las Campanas Observatory. Quite a dramatic picture. So why is this important? Why should you care? Well, among other things, supernovae kind of drive galaxies. They influence their energy balance, structure, and chemical makeup. Stellar death, supernova, can actually trigger star formation. So these blast waves run into molecular clouds and cause stars to form. Stars are a significant source of dust, and this is important as we try to look deeper and deeper into the universe, and there's more and more obscuring dust. So understanding the nature of it and how it obscures our vision is important. Supernovae produce a variety of exotic objects that many of us like to talk about, such as neutron stars, black holes, and some gamma ray bursts. Supernovae also produce copious neutrinos. We're going to talk about that later in the slide. This is going to be key to alerting us on when the next supernova happens in the Milky Way galaxy. Supernovae are progenitors of gravitational wave systems. That's getting a lot of lot of news these days because we now have systems, thanks to advanced LIGO and Virgo and new systems coming online that can detect these gravitational waves. The supernova explosions themselves produce gravitational waves, and that'll actually be a key metric by which to understand how the star explodes, which I'll go into later. And finally, perhaps most important to us, they manufacture the heavy elements that make life possible. So thus, I argue it's terribly important to understand this fundamental process that goes on in our universe. So, the iron in our blood, the calcium in our bones, and the oxygen we breathe. Love that oxygen. That's all being manufactured in these stellar explosions. Okay, so what are there are many questions one can posit about supernova explosions. The one I'm focusing on in my research, and that I'll touch on here, are what are the types of stars that explode? Okay. What was interesting that prior to 1987, we thought that the natural progenitor system of supernova explosions would be red supergiant stars. But in fact, that image of the progenitor of 1987A, which was the first time actually that we imaged the star directly before exploding, was a blue supergiant. Then, of course, the theorists retroactively predicted that blue supergiants could lead to supernova explosions. But since then, we found other stars that weren't supposed to explode, like yellow supergiant stars. Okay. So this is an important aspect of understanding supernovae. Next, how do stars explode?
Dr. Dan, I have a question in the chat, if you don't mind.
Okay.
So Joanne's asking, it went up. Are we seeing it in real time?
Okay, I will get to that. So
okay,
just
good. Thank you.
Hold up. But I'll just throw it there for general context. Of course, light has a finite velocity, and it takes time for that light to travel the vast distances of space. So for instance, if we saw Betelgeuse exploding tonight, okay, it had actually exploded how long previous to that? Well, I think the most recent estimated Betelgeuse is around 200 parsecs. Multiply that by 3 to get it into light years, right? So that means it would have exploded over 600 years ago before it came here. Does that make sense? Does that answer the question?
Yeah. Yes.
Okay. We'll be talking also about much more distant supernovae, and I'm looking at the question. We're seeing something a few zillion years ago. Well, not quite zillion, but it may be millions or tens of millions or hundreds of millions of years previously. That's right. All right. Oh, I like to show this animation to remind people of just how big stars can be. All right. I don't know the background, but even I get a kick out of this animation. I think the sound is part of what makes it so much fun. So we're passing through our neighborly planets. There's Venus, there's Earth. We love Earth. Don't want to go anywhere else. The best place to live. It's Neptune, Saturn without the rings, which you can see is kind of comparable in size to Jupiter, the biggest planet. And then we scale back and there's the sun. Now, so often people are surprised that sun is not the biggest star. There's actually a much bigger star. There's Sirius A, the brightest star in the sky. That's not the biggest star. Pollux, orange giants. Now you notice the colors changing. Larger stars tend to be cooler, give off more red colors. Rigel, here's a blue supergiant. Now we're going to scale back even more. Pistol star, blue hypergiant. Antares A, a red supergiant. Mu Cephei, another red supergiant. And VY Canis Majoris, one of the largest stars in the universe. And then the fun part, there's the size of Earth. Now for perspective, imagining that star exploding. That's the context for our discussion today. Okay. One thing I also like to make clear to people is that the sun will not explode as a supernova. There's actually a mass threshold for which needs to be reached before the fusion at the core can get to the level where a core collapse is triggered. So a reminder that, the mass of the star largely dictates how long it will live. There are other factors, the composition, metallicity, we say, its binary companion can change it, but broadly speaking, the mass can kind of translate into how long it will live. So our sun, right, one solar mass in terms of our sun, will live about 10 billion years. And it will end its life as a white dwarf. Once you start getting above 8 to 10 solar masses, and then notice the dramatic change in lifetime. We're talking now tens of millions of years. Okay. Once you get above 10 solar mass, this is the range of which supernova explosions begin to proceed. Okay. So again, don't worry, you can go to bed not worrying that the sun will explode. Okay. The sun will expand and consume the Earth most likely, another 5 billion years from now. That's another thing, but at least it won't explode as a supernova. And a reminder, so beyond the mass dictating the fate, there are two different fates for what we call core collapse. So once you get to the 10 solar mass range and above, this collapses down to a neutron star. Once you start getting above 20 to 25 solar masses, this is where collapse can proceed to a black hole. There are caveats to this, whereas we're finding that the models are making it possible that you can have even larger stars still collapse down to a neutron star, or you can have black holes from less massive stars. Okay, but all things granted, generally it's fair to say that stars that are below 25 solar masses will generally form neutron stars, and those above with black holes. Okay. Once you start getting to very high mass, 100 solar mass and beyond, then other kind of exotic processes can take place. I won't get into that today.
Dr. Dan, you have a
Yes.
question in the chat. How do astronomers figure out the size of stars?
Oh, okay. Well, there's a lot that goes into that. And if they're nearby, we can actually kind of make resolved measurements, but that's very hard to do. Most stars tend to be unresolved, but we're very good at estimating masses when stars are in binary orbits. And once we know masses and velocities, we can make estimates of their sizes with physics, because we know the compositions of stars. And we have good scaling effects on how that gas is distributed, and we can make very good estimates on the sizes of stars. Any other questions? Okay.
Thanks. And how do astronomers determine how many light years away things are?
The distances to stars.
Yeah.
You're asking.
Yeah.
There are many different strategies to do that. For the nearest stars, one of the most robust methods is that of parallax. So the same thing that if you stick your finger in front of your face and you blink between your two eyes, you see how the finger goes back and forth. If you put it right up against your nose, the amount that finger goes back and forth is much larger than when it's far away. Okay. So that's the same thing we can do with stars as the Earth goes around the sun. So the position that a star is viewed on in the sky from one part of our orbit to the opposite side, that's a parallax of the star, and we can use that to make an estimate to the distance. That works for only up to a certain distance. Then there are other methods that we can use to measure distances. But important to say, distance remains one of the most challenging things to do in astronomy, period. Okay.
Like on Earth, from one scene to another is measured in miles, and Luna is measured in feet. But that's hard to understand.
Yeah.
Thank you.
Yeah. So Daniel, maybe we take that up for an astro school one day and we can cover those topics in more detail. Thanks for the question.
Very good. All right, just going back to all the excitement over gravitational wave detections. So what Nobel Prize, the Nobel Prize went to the discovery of merging black holes. Those two black holes that merge were independently formed in supernova explosions. Okay. Likewise, 2 years later, there is the exciting discovery of merging neutron stars. Neutron stars are, this has elicited a lot of excitement in the astro community because they're associated with electromagnetic radiation. Unlike merging black holes, which are kind of dark, right? They don't have a fireworks display. At least we don't think they do. We haven't been able to observe that. Merging neutron stars do emit in the electromagnetic radiation. We're able to follow up from X-ray, optical, infrared, and radio. So again, each of these neutron stars formed in supernova explosions. And so it's actually non-trivial to think of the progenitor system, okay, that would allow two stars to be close enough to independently explode and to keep those two remnants, the cores, the neutron stars, close enough in orbit to then merge within a Hubble time. All right, without going deep into the physics, let me just give you a cartoon notion of what happens when a star explodes. It begins as mostly hydrogen, about 70% hydrogen, 20-ish% helium, maybe 25, and then other trace elements. And it begins with fusing hydrogen in its core, and it spends most of its life fusing hydrogen in its core into helium. But at some point, the core no longer has enough hydrogen to maintain the fusion, so it has to go to the next heaviest element, which is the helium, and it begins to burn the helium. The hydrogen then gets pushed out to a shell, and then when it exhausts the helium in the core, it goes to the next element. And so what happens is this iron-skinned interior develops, where hydrogen is at the outermost layer. There's helium, carbon, neon, oxygen, silicon, and iron. Now, something special happens when iron is fused. Okay? Unlike the other elements, silicon, oxygen, etc., when you fuse those elements, okay, it produces energy. When you fuse iron, it's actually endothermic. It needs energy for you to put it together. And all of a sudden, the radiative pressure that was holding the star up against gravity is lost. Okay? This is what's being depicted here. This is when the collapse ensues. Okay? And all those years of fusing these elements in the core in iron gets blowed up, for lack of a better expression, and it breaks down into protons, neutrons, electrons. Now those protons get captured on, those electrons get captured onto the protons to form neutrons. And there's high energy gamma rays that disintegrate other elements in the interior. So what you're left with is that neutron-rich core. That's what becomes the neutron star. And it collapses down to a part where the neutrons say, hey, we can't get any closer. Okay? And at that point, there's a rebounding shock that from the material that comes up and bounces off, because those neutrons say we can't get any closer. So for years, it was thought that this bounce and this rebound was enough for the star to explode. But years of simulations were unable to make the star explode. They always continued to collapse in the simulations under spherical conditions. So it's been, since the 60s, attempting to understand what mechanism, okay, what are the physics that allow the explosion to proceed. The most popular idea is that neutrinos that are produced in this process of core collapse, and I mentioned the production of neutrons as electrons are collected onto protons, those produce neutrinos. There's lots of neutrinos that are produced, and I have a slide on neutrinos in a moment, don't worry. Just think of it as a subatomic particle. Like you've heard the word electron most likely, right? So it's just another kind of particle, this high energy, almost no mass, called a neutrino. And normally neutrinos go through no problem. There are many neutrinos passing through us right now, but under the intense temperatures and densities of a collapsing star, the neutrinos have some kind of opacity. They help in the explosion. Okay. And this slide is just showing some simulation work where these neutrinos heat, they make hot spots. And there's these convective flows that get set up that try to help the star to explode. On the left is an alternative idea where if there's enough rotation in the core, charged particles are associated with magnetic fields. Magnetic fields can produce a new mechanism for the explosion to proceed. Okay. So the takeaway points here is that under spherical conditions, it doesn't seem like the explosion can proceed. Something else needs to contribute. And we think that it's, in most circumstances, the neutrinos, but we also think magnetic fields or other mechanisms may contribute. That's my research, trying to understand right at the core of the star what's happening. Okay. Oh, here's my slide. What the heck is a neutrino? This is a slide that my wife said I had to include because she got lost whenever I gave this talk in front of her. So as I said, a neutrino is a subatomic particle, and it's very similar to an electron, but it has no electrical charge and a very, very, very small mass that's 500,000 times less than the electron. Okay, so here's a map of kind of particle physics, and somebody has cleverly made these cartoons to kind of mimic what their properties are. So these are kind of like ghost-like particles, the neutrinos, because they don't really interact with anything. Photons, people have probably heard of photons. They provide light, right? So, etc. So neutrinos end up being one of the most abundant particles in the universe. But because they have very little interaction with matter, they are incredibly difficult to detect. So here's a fun fact. Approximately 100 trillion neutrinos are passing through your body each second right now. Just soak in the neutrinos. Most of those are being provided by the sun. Okay? But thankfully, there's not much cross section. And here's even, somebody asked me this, well, how often would an interaction happen? Well, we expect on average one interaction with the human body over 100 years. So not much. So experiments that want to study neutrinos need a lot of material, right? So they have vast tanks of detectors, and they can make that interaction go up to about 300 interactions a day. And I'll give you an example of that later.
Dr. Dan, there is a question in the chat.
Okay.
Does dark matter have any possible contribution?
Does dark matter have a contribution to the supernova explosion? No. No. So dark matter permeate. Yes. It doesn't interact except with gravity. I've heard some fringe ideas of dark matter these cores leading to dark matter cores. I'm honestly stretching my imagination trying to make that work, but dark matter, let's just say full stop, dark matter does not participate in the core collapse process. Dark matter is more important at larger cosmic scales in influencing the gravitational pull of galaxies.
So what you're saying is relative to supernovae, it doesn't matter.
Correct. Correct. Okay.
What
Great.
about regular matter? I mean, you talked about asymmetry due to these other things. Does an asymmetric mass in proximity to a large star contribute to possible supernovas?
So on that point, if I go back, the breaking of symmetry is what we think is key. Where is that symmetry broken? Here it could be uneven neutrino heating, could be magneto-rotational jets. I think what you're getting at is another possibility, which is the progenitor star itself. So you can have a seed of a spherical explosion, but the progenitor system, which has been really kind of shaken up in the terminal phases approaching core collapse, because there's a lot of these, if I go through here, neon burning lasts about a year, oxygen burning, a month. This silicon burning lasts a day. And as it transitions between those burning phases, there's turbulence set up. So asymmetry in the distribution of material may also be an important part of how the explosion proceeds. So great question. Okay, great. I don't have my, can somebody give me a time right now? I don't have my watch up, so I just want to make sure I don't go too far over.
Oh, no, you're good. It's only 5 to 8, so
Okay, all right.
yeah, you're doing what great.
Okay. So now I've given you the background for what happens with a supernova. Let's talk about observations. When galactic supernovae occur, so this is what is happening in our own Milky Way galaxy, they may last for many months and be seen with the naked eye, even during the day. So in the case of 87A, that's in the Large Magellanic Cloud. That's a satellite galaxy to the Milky Way, so it wasn't incredibly bright, okay? But it was bright enough to be seen by naked eye if you knew where to look. Okay? There are other cases of where it was very bright. Here's an etching of Tycho Brahe, or Tycho Brahe, who observed the supernova of 1572. And again, you could have a whole lecture on Tycho Brahe, who was a very interesting, colorful character of astronomy, of which we have many nonetheless. The cool thing about this is that we have historical records of how bright it was over time, and we can look at that location now and see what it looks like. So here is a light curve. This is time, and this is, visual magnitude of that supernova reconstructed from Chinese, Korean, and other European records. The peak magnitude is minus 4.5. For reference, Venus is around minus 4.2. Okay? So try to imagine back in the days when people paid more attention in the night sky because it wasn't polluted by light pollution, right? And all of a sudden a new source being visible, okay? And potentially visible during the day. This is also helpful to understand the time scale for a supernova explosion. So this is with respect to an inferred explosion epoch. It generally takes a few weeks to reach maximum light, and then it fades within the upcoming months to year. It depends on how nearby it is for how long we can track it. It also depends on the type of explosion for how long we can track it. But this gives you a sense of the time scale of how long it takes to rise and then fade. So a rise is much more quickly than it fades.
Dr. Dan, there's a question in the chat.
Yes.
Kind of relative to your comment about the light pollution. Could a supernova be the star of Bethlehem?
I've heard that thought of before. There is no credible evidence backing up that. It's most likely to have been a nova and even that it hasn't been verified for sure. But I do like that idea of it being associated with a supernova, but most likely not. And how we can actually follow that up, if you look at historical records, you can get a sense of the brightness. Was it there at the right time? There's a little bit of complications with calendars, making sure everything is lined up. And then we can also look for supernova remnants, the debris fields, which I'm going to get to right now, actually. So this is what the region of that supernova looks like today. This is a composite image made from optical, which is showing the stars, and X-ray. And the X-ray band has been divided up into its various energy regions to give the different colors that you see. This supernova was of a type 1A, and different supernovae have classifications. Type 1A means the original star was not a massive star, but it was actually a white dwarf that gained material from a companion star, or there were two white dwarf stars that came together. My talk is focused on massive star explosions. To talk about these other types of explosions, type 1A, that's another lecture altogether. Here I'm showing what Tycho Brahe wrote in his book about the event. He really zhuzhed it up, as it were, really kind of made it sound incredible. A miracle indeed, either the greatest of all that have occurred in the whole range of nature since the beginning of the world, or one that is certainly to be classed with those attested by the holy oracles, the staying of the sun in its course in answer to the prayers of Joshua in the darkening of the sun's face at the time of crucifixion. So it was really big deal. Johannes Kepler, another interesting character who worked for Tycho Brahe. Some suspected that Kepler poisoned Tycho Brahe because within a year of them working with one another, there was reports of them getting into arguments and Tycho Brahe dying. So they thought Kepler had poisoned him. But Tycho Brahe's body was exhumed twice, and Kepler's been cleared of wrongdoing both times. Anyhow, in 1604, there was another galactic supernova. We now refer to this as Kepler's supernova remnant. And here again, it's a combination of optical and X-ray. Optical is the more resolved material in yellowish, and the other colors are in X-ray. Kepler was a little bit more modest. The star's significance is a difficult matter to establish, so we can be sure of only one thing, that either the star signifies nothing at all for mankind, or it signifies something of such exalted importance that is beyond the grasp and understanding of any man or woman. So he kind of played it more even than Tycho. And here is another light curve, this one of 1604. You can see that it wasn't as bright. It was the same type of explosion, type 1A. So the difference in brightness is attributable to the fact that Kepler supernova was more distant. Here is the remains of a star that exploded about 340 years ago. It's in the constellation Cassiopeia, and I saw that as one of the constellations that needed to be sketched. It's my favorite constellation. The A comes from the fact that it was first discovered as a radio source, and it was the first radio source in Cassiopeia, so Cassiopeia A. This image is in optical, taken with the Hubble Space Telescope. Red signifies sulfur-emitting material, green is oxygen, and this purpley blue stuff is hydrogen and nitrogen material. We don't know the exact date because there was no credible viewing of the actual supernova explosion. So we actually watch the material expand with time, and we can make an estimate of when it all came back to the center. We can roll back the clock, as it were. My work is creating three-dimensional reconstructions of supernovae and doing a sort of bomb squad investigation to understand what we can learn from the morphology. So how the debris is arranged, how can we trace this back to the original explosion dynamics using, for instance, those simulations that I showed earlier on. Many things to unpack here. Most important is that it's not random. There's large scale coherent structure in the debris, and that was frozen in shortly after the explosion. Here's a Mercator map of what we see here. So it's kind of like a map of the world, right? And we see continents of ejecta, the stellar debris gas. You can see that they're arranged in circles, right? The crab, M1. Everybody's familiar with the crab. This is another remnant for which we completed a three-dimensional reconstruction recently. If you're interested, you can go to this paper or you can contact me. I can give you this animation directly. This is not a simulation. This is made out of real observations of the Crab Nebula. And now all of a sudden, instead of being stuck to just looking at it in the plane of the sky from Earth, we can look at it from any angle that we want. And the thing to take away is that there is large scale structure, but it's not as, let's say, there are smaller structures here than there is in Cassiopeia A, and that we think reflects the progenitor system, the type of star that was there before the explosion. It may also be in part by how the star exploded. Oh, now we're going to go inside, stick our head inside the Crab Nebula. All right, I'm going to move on. By the way, I don't have it on me, but there is a astronomer in the UK that makes sculptures with crystal, and he reached out to us to be able to make this with the Crab Nebula. So you can hold the Crab Nebula. It's a 3D model, and they use lasers to etch in little dots, and they recreated the Crab Nebula inside of this. So he gave me a free one on the condition that I would advertise it. So I encourage you to crystalnebula.co.uk if you're interested in this.
Dr. Dan, Victor
Yes.
has a question in the chat. Is that 3D representation derived from Doppler red and blue shift?
Yes. Yes, whoever asked that is spot on exactly with how this was created, right? So in a nutshell, the material, it all started from a center point, the original star, and then it exploded such that the material that's furthest out would be moving proportionately faster than material that's closer in. So if we measure the velocity, which is the Doppler shift, that's exactly right, because just like sound changes depending on whether it's coming towards you or away, as a car goes by, light does the same thing. So if it's approaching you, it shifts towards blue wavelength. It's going away, it's red wavelengths. We take spectra of all the filaments of the crab, right? And then we can determine the velocities, and then that gets translated into a distance away from the plane of the sky. Does that answer the question?
Yes, thank you.
Great. Okay, so let's now talk about the Supernova Early Warning System, which is part of what I'm here to advertise to you. The next nearby core collapse supernova, so ones that come from massive stars, will produce neutrinos, gravitational waves, and electromagnetic radiation. And we are only now in an era where we are sensitive to all of these things. This is what we call multi-messenger astronomy. Phil, that's the first thing that you read off. So I'm interested in multi-messenger astronomy. And what that means is it's not just electromagnetic radiation anymore. There can be other messengers, other information passing things, gravitational waves and neutrinos. The thing is that neutrinos, because they can stream through material so easily, neutrinos will be the first to arrive at Earth before the electromagnetic radiation. Maybe you've heard that a photon at the center of the sun takes tens of thousands of years to diffuse out because it's so opaque and there's this random walk that it needs to go through, right? So that's the same with a supernova explosion. The radiation at the core takes time for it to get out to the edge of the star, but the neutrinos go through no problem. So if we look here, this is in log time, which is not the most convenient, but think of it as, you know, this is just, you know, in powers of 10 in terms of seconds. So the neutrinos, which here, this is what these things are, the neutrinos, they have much more energy. This is in terms of energy, and they arrive, right, much sooner than shock breakout. This is electromagnetic radiation. Okay. Now, the gravitational wave radiation will come not long after the neutrinos, but we don't know how strong it's going to be. And unlike LIGO, which is going to trigger, you know, on the detections of merging black holes, we don't know if it's going to be able to be sensitive enough to act on a core collapse supernova. But the neutrino signal will be strong and obvious and clear. This is the first alert. So I'm part of what we call the Supernova Early Warning System, which is a network of, let's see here, I'll go here. Yeah, it's a network of neutrino facilities that share information so that we can have a confident, you know, broadcast alert if the neutrinos are detected. So let me phrase it like this. If the next nearby star to explode is Betelgeuse, it's going to be obvious and you'll see it in any detector. But if it's much further out, the change in detection for any one of these systems may be subtle, right? So confidence in one system is not strong, but if you have multiple systems all verifying a change in their experiment, then we have, you know, much higher confidence overall that the neutrino is due to supernova.
Hey, Dan, I have a question.
Yes.
So when these detectors pick up this increased neutrino activity from all over the world, and pretty much, I would imagine, almost exactly at the same time, out to several zeros, decimal places, how do you take that information and triangulate it in such a way that you could target where the supernova occurred?
So you're getting ahead of me, but that's great lead in, right? So exactly the same way that LIGO and Virgo are able to triangulate gravitational waves based on the delay between the different facilities, the hope is to be able to do that with neutrino facilities as well. That's exactly right. And let's see, did I miss anything here? Okay, this is just for fun. I don't want to take up too much time. I could talk a while. Let me get back to your question in a moment, but let me just quickly go over these slides. During 1987A, there was about 20 neutrinos that were detected. Okay. Now, since that time, the technology has increased considerably, and the number of neutrino facilities has increased considerably. So instead of 20 neutrinos, we're likely to detect thousands of neutrinos. And there's much more science that can be done as a result. Here is a listing of the various facilities and the numbers of neutrinos that they may detect depending on different masses of stars, assuming a distance of 10 kiloparsecs. Let me just say that if you ever get a chance, go visit one of these neutrino facilities. They're in really cool places like the Snow Lab in Sudbury, where you go 2 kilometers underground in a mine. You get to do the gear. So that was me visiting one of the neutrino facilities. Here's Super Kamiokande in Japan. If you can see, what this is, this is normally filled with water, but they had to replace the photo multiplier tubes. These are sensitive to light that gets produced as a neutrino interacts with the water here. Normally this is filled, but you can see them in the life raft. They're going around checking, replacing these photomultiplier tubes. Interesting story here. Some time ago, as they were refilling the tank, one of these tubes shattered and sent out a shock wave that destroyed almost all of the detectors, and they had to replace it. That was a real mess, but they replaced it and it's working actively now. Okay, so I
Doctor-
taught. Oh, yes.
I'm sorry, Dr. Dan, there's a question in the chat. Have you ever gotten false alarms for faraway supernovas because the signal is so subtle?
Hey, that's an excellent question. Let's see here in this slide. SNEWS has been operating since 2005, but has never produced an alert. Okay. Now, what's interesting is, why is that, right?
So we should check to see if it's plugged in.
Okay, without going into too many details, it hasn't produced alert because our threshold has been very conservative. We don't want to send out a false alarm. So for it to be recognized as a real signal, it needs to be loud and clear. We recently got money from the National Science Foundation to upgrade to 2.0, where we begin to reduce that threshold. And there's the potential to broadcast false alarms, but at the opportunity of going after different phenomena or more distant events, right? So you increase the amount of events you may be sensitive to, but you also increase the contamination as well. So we're in the middle of adjusting those parameters, and that may be person to person, who may be, some only want the real thing for sure. Some are willing to take a chance and act on false alarms. Great question. Okay, so this is the information that SNEWS wants to provide for observers. And this is where you guys and girls and anybody else comes in, okay? In the sense of SNEWS will tell you that something is happening. And our hope is that shortly afterwards, we'll have a localization. And that's made through triangulation, as Phil had asked, right? And then a little while later, we hope to provide some information about the nature of the explosion. So for instance, if it collapses down to a neutron star or a black hole, produces a different neutrino light curve, and that can actually help us in how to pursue it. If it collapses down to a black hole, it's likely to not have a big boom associated with it because it's a collapse. So we may be actually looking for a winking star, something that pops out of the sky as opposed to becoming very luminous. Right? So that information can help guide the follow-up strategy. And what we're doing now, and it started with an alliance with the AAVSO, but we're looking for anybody that wants to help, is developing a list of candidate stars. So the stars that are most likely to explode as supernovae. Remember, there is a time delay between when the star explodes and we receive the neutrinos and when the first electromagnetic radiation arrives at Earth. That delay may be anywhere from minutes for a very compact star to several hours or a day. So the moment that we get the neutrino alert, we want to be on sky monitoring through a combination of wide field monitoring to see anything, with focused investigation of stars, so that we can almost watch in real time as the star changes, and that what we call shock breakout, the moment that shock wave makes its way through the stellar interior and exit through the surface of the star and has this bright UV X-ray emission. Here we're showing various attempts to identify stars that are most likely to explode as supernovae. This is not actually an easy task, and we have multiple people doing this, trying to come up with the candidate star list. Now, this is made of largely red supergiants, but as we discussed earlier, it needn't necessarily be a red supergiant. Could be a blue supergiant, could be a Wolf-Rayet star, could be a yellow supergiant, right? So I've been advocating this risk mitigation strategy where we have intensive monitoring of likely candidates, and that's where strength in numbers happens. So there's a lot of professional groups out there that have access to surveys that will be mapping the sky. You know, for instance, the Zwicky Transient Facility can map the whole sky in 4 or 5 hours, the whole visible sky. But you know, as they're pointing in one location, the explosion may be happening somewhere else, or they may be clouded out that night. For time domain astronomy, you always have strength in numbers in geographic diversity. So that's where it helps to have as many people, as many eyes on the sky as possible.
Hey, Danny, I gotta go back. I got back one quick. So are the neutrinos released at least before the supernova explosion happens? Is there a large neutrino release? Is that why there's a difference? Because the neutrinos are traveling at the speed of light, correct? And
just below the speed of light, but yes, yes.
And the light is traveling at the speed of light. So I would think for all practical purposes in astronomical rounding, that there wouldn't be a delay. The visible part would be the same time as the neutrino time, unless the neutrinos were released prior to the explosion and some increased number. Am I way off mark here?
No, I never had a crowd that asked so many physics questions. So let's go down to it. All right. Maybe this simulation is going to help. Okay. So the moment that the core collapses, actually, I should just play it. The moment that the core collapses, that's when there's an intense burst of neutrinos that are produced. Okay. Then there is a delay in that shock making its way through the star. Okay. And that delay, like I said, may be minutes to hours.
Okay.
Do you see it fighting? Now, this time scale is within a second. Okay, this whole simulation is not in real time. It may take upwards of a second. But then as this bounce shock is fighting through all this material that's falling above it, right? It's a collapsing, and then the shock has to push through the star. Okay, so do you see what I'm getting at?
Yes.
There's the collapse, the proto-neutron star is formed, and there's this burst of neutrinos. That's what arrives first. Okay, and it doesn't worry about passing through the material, whereas there's this bounce shock, and then that takes time to propagate through the star. So it's a subtle delay, but it's large enough. And remember, the star is large, okay? So that shock, it's not moving at the speed of light, okay? It's moving, tens of thousands of kilometers per second, but certainly not 300,000 kilometers per second, right? Yep. So that difference is what we're trying to leverage with the Supernova Early Warning System.
Dr. Dan, Arjun's trying to verify, since the neutrinos are high energy, they don't have a higher probability of interacting than other normal energy ones. Arjun, do you want to add on to that?
No, that's my question.
Yeah, well, remember here that these have very little mass, okay, and so their cross section of interaction is very small. That's the best way to understand it. Okay. All right, let me get back to where I was, and now we're at 8:20.
Well, before you
wow.
go forward, there was another question about the false alarms.
Okay.
And that is, what other events might create a false alarm, and can any other high energy far away subtle signals be detected by the supernova detectors? Remember the slide you showed us with the supernova detectors with the people in the raft?
That's right. Oh, sorry. Okay, Wilbur's gone out the door now, so we're fine.
Okay.
Yeah, so there are other astrophysical processes that may produce neutrinos. That's right, and there's that's why the field of multi-messenger astronomy is picking up. So more recently, it was thought that there was a distant active galactic nucleus, which is a galaxy that has a lot of energy and it's being powered by a supermassive black hole with jets at its center. There is a thought that there is a neutrino detected from an astrophysical source, but largely the neutrinos that we detect are from the sun. The hope is to be able to be sensitive to other sources. Another one may be type 1a supernovae, but they don't produce neutrinos nearly as much as the core collapse explosion. Okay, there are other types of explosions, but so pair instability supernova, again exotic, much higher mass. Basically, it's the core collapse supernova that is the most likely because they are so powerful and much more frequently occurring than other events. Okay, great. Okay, so I see I have many more slides, and I'll try to keep this at a good pace, and I don't want to bore people. I don't want to be that guest that drags it out too long. I just want to emphasize the importance of volunteer astronomers. Sometimes you're referred to as amateurs. I just say volunteer. You don't call a part-time firefighter an amateur firefighter. No, they're volunteers. So it's like a volunteer astronomer. In this case, Victor Busso here was setting up a new camera on his telescope, and all he did was point to the galaxy that happened to be overhead at the time and just had the camera continuously reading out. And he was fortunate enough to get these exposures that captured the supernova as it was happening. And he was capturing the supernova as it exploded, as that shock breakout occurred. So as that shock made its way through the star. Here's the light curve. These are his contributions. And then you can see the knucklehead professional astronomers weren't there till like a day later for when the supernova was occurring. Okay. So again, strength in numbers and as many eyes in the sky and geographic diversity always wins out. Now, what we've never been able to do is to have a precise timing for when that neutrino burst happened and the shock breakout. That timing of how long it takes the shock to make its way through the star is incredibly important. Okay, so finally, we can't be waiting around forever for the next galactic supernova because it may happen tonight as far as when it's observable from Earth, or it may happen 100 years from now. So what do we do in the meantime? Well, we can observe extragalactic supernovae, which are happening all the time. Here's a couple of examples of searches for supernovae. This was operating before the Pan-STARRS survey. I was a part of that. The SASN survey, the Zwicky Transient Facility that's operating now out of California, and then excellent contributions from volunteers like Stu Parker, who I work with, who by day is a dairy farmer in New Zealand, has over 200 cows, but by night has a real sophisticated setup and has discovered over 150 supernovae himself. Hey, here's a question. Can you spot the supernova developing in these 4 images? There it is there, right in the center. Okay. Now, obviously, we don't do this by eye nowadays, but before it used to be. I bring to your attention Reverend Robert Evans, who holds the record for most visual discoveries of supernovae. Robert was amazing in that he had a photographic memory of galaxies, and he could observe 50 galaxies an hour when they were scattered around the sky, or 100 galaxies an hour, 120 galaxies an hour in Virgo, he could point to the field and by memory tell if there is a new source or not.
Wow.
Right? That's incredible to me. And no, none of these go-to mounts, man. No, he was doing everything, moving everything by hand. Here is a number of postage stamps of extragalactic supernovae. One of the challenges is that they only are these unresolved spots, and it can be hard to, know whether a source is new. So that's why we do this technique of imaging a source, coming up with a template, and then returning to it some days or weeks or months later, and then doing a subtraction to see if there's a residual. How many supernovae are going off? Well, supernovae occur approximately 1 per galaxy per century. And if you work out the numbers, you do it, all things even, there's basically 1 supernova every second in the universe going off. Okay, now, most of those supernovae are too distant to see, okay? But we're getting a lot better at capturing them. This is images from Stu. This never gets old to me. Here is a template image. So this is before the supernova and then afterwards.
Wow.
Okay. Now, maybe that's not impressive for some people, but you have to appreciate this is an entire galaxy, hundreds of millions of stars, more or less. And then all of a sudden, in this diffuse arrangement, there's one of those stars that begins to rival the brightness of the galaxy. In many instances, we have the supernova that's brighter than the entire host galaxy, right? A supernova can be brighter than billions of stars put together. Here's a recent history. Oh, question?
I'm sorry to interrupt. Yeah, there was a question in the chat about the release of neutrinos. Is the sudden release of copious neutrinos during the core collapse due to a rapid increase of fusion from the core?
So remember, it's the in full, as briefly as I can say, the neutrinos are produced through largely 2 processes. One, electrons being captured by protons, forming neutrons and neutrinos, and photodissociation. So these are high energy gamma rays that are splitting up nuclei and producing neutrinos. Those are the processes that are producing the neutrinos, not the fusion itself. All right, discovering supernovae. And this is now where I'm going to get into another project called Refit that Chuck has been helping with. So here is a time frame of how many supernovae we've been able to discover over the years. And you can see with CCDs, charge coupled devices, detectors that have been able to increase the efficiency. This is an older image, and if we update it, you can see nowadays we can find many thousands of supernovae. In the not too distant future, your taxpayer money is going towards the construction of the Vera Rubin Observatory that's going to conduct the legacy survey of space and time. This is going to be a revolution in time domain astronomy. Here is a plot that should drive that home for you. Here is, where we're at in terms of all the supernovae between 1996 and 2002 are going to be about 100,000. Whereas when LSST is operating, it may find upwards of 1 million supernovae per year, right? So all of a sudden, we're going to have a lot of new data to have to process. And here is how it's done. This is what I was describing earlier. This is the template image. Then a science image is taken sometime later, and you subtract the template from the science after adjusting for, seeing differences, integration time differences. There's fancy ways that we can do that if there's a residual, okay? This large the legacy survey of space and time is going to be able to automatically detect if there's a residual, measure how bright it is, and send an alert to a stream all within about 60 seconds of that exposure happening. So there's going to be a steady stream of alerts coming for changes in brightness.
Where will that be?
That's going to be in Chile, southern sky. So to put pictures to it, if that's what the data rate, if the data rate now or then is like a faucet, okay, in the not too distant future, this is what it's going to be like. So how we're trying to help is we've developed this recommendation device, the recommender engine for intelligent transient tracking. And what this is for anybody, professional or volunteer, if you have some telescope time and you want to contribute to the worldwide effort to watching the universe and monitoring for changes and contributing scientific data that can be published, right? You go to this platform, which right now is a website. Hopefully one day it'll be an app on a phone, and it will guide you towards science-rich opportunities so that you don't need to be actively following anything that's happening all the time. But it's like Netflix, right? You turn that on and it automatically tells you what it thinks your next favorite movie is going to be or TV show. We're trying to do the same thing to make it simple. We will be ingesting all of the alerts of the All Sky survey. We then have to do some analysis and interpreting how that light curve is evolving and how it's going to evolve into the future. That's where our forecasting comes in. And then we make priority lists that we broadcast out to users. And those users, if they're able to, act on the recommendations, take data, and we provide hopefully an easy platform that you could upload that to us directly so that it can inform refit to improve the forecast and continue the cycle. Here's a screenshot of what the website looks like right now. Here's the light curve of the evolving transient. Here's our forecast with uncertainty regions, and this is what refit thinks it's going to be. But of course, it could continue to go up. It could continue to go down. So we need a measurement to be sure. We also like to have fun names because names are much more complicated now because they find so many supernovae. It may be ZTF21AQVWAY. So why not instead have a fun auto-generated name like Modest Awesome Hawking? Here's a transit light curve. Yes, that's what I described. I'll skip ahead there. Here is a collection of the beta testers currently helping us with refit. There's Chuck there who reached out, and he's, for good or bad, the reason that I'm here, helped connect me with your group. We are looking for additional beta testers right now, although we're trying to keep it contained until we're ready for full opening to work out the kinks on the website. Oh, and I'm also included on that list as well. I bought my own telescope, anteed up, and to try and show that I have some skin in the game. I want to use this slide to show that you don't need to have, a dark sky access with, half-meter telescope to contribute science. Look at here. So this is the Astro Boilermaker telescope that I use in my backyard, Bortle Class 2 in downtown Lafayette, Indiana, versus a professional telescope located on a mountaintop observatory in Hawaii. See mine nicely focused. I can clearly identify the supernova from the host galaxy, and their galaxy, which was not in their image, which was not tracking properly, right? I showed this to one of my colleagues, and she said, "You're going to get somebody fired because of this." So again, technology has really made it possible for volunteers to contribute valuable scientific data.
There's a question that says, will LSST end the discoveries of willing astronomers?
I'm sorry, I didn't understand that. Will LSST what?
End the discoveries of willing astronomers.
Oh, so that is an interesting question. It will definitely take away, I mean, we're already at the point where discovering supernovae before the surveys is a challenge. And part of the motivation for this is to find ways for volunteers to contribute towards, because now they may not necessarily discover the supernova, but there's what use is the supernova unless you have the science behind it. And the science comes from a good light curve, well-sampled light curve, right? So that's where the volunteers can be able to contribute more, not just the discovery, but the science behind it. But indeed, yes, it's being harder and harder for amateur volunteers to contribute novel discoveries of supernovae.
Hey, Danny, we're at about 8:40.
And I'm done. I'm done.
You're done.
I just wanted to show that story in my backyard. I couldn't even polar align the telescope to be able to get this, thanks to off-axis guiding. And here's the final slide. Okay, I just wanted to drive home the points that supernovae are, fundamental in our universe. I hope I made some excitement about time domain astronomy, and citizen scientists, volunteer astronomers can contribute important science. If you're interested in any way about what I was talking about today, here's some contact information. Please don't be shy about emailing me.
There's one
Thanks
last
very
question in the chat about the name choosing process. What is that? Or is there, do you know?
Oh, the names that we chose were completely auto-generated. We have lists of adjectives and lists of famous names. And then whenever there's a new recommendation made, the name gets auto-generated.
Well, thank you very much. Danny, so to Daniel's question earlier about going back to Robinson Nature Center for this meeting, if we were at Robinson Nature Center, we would have to be out of the building at 9 o'clock. So the people that work there go home. With Zoom, we don't have that limitation, and every month we go past 9 o'clock because of the quality of the questions, and then because of the questions are generated because of the quality of the presentations. So so this is another reason to keep these meetings on Zoom and not be in a place where our time is finite for sure. So Danny, I don't know if you'd be willing to stay on for a little while longer and maybe catch some questions after the official end of the meeting, or if you have to run.
No, I'm here, and I'm sorry if I went a little long, but
you're fine. The people. This is
great questions, great conversation. Yes,
you're here to inform and educate, and entertain, and the whole purpose of this is for people to ask their questions and really get as much out of your expertise and experiences as possible. So couldn't thank you enough. So we're going to formally end it here and put you on hold until a little bit later, and when you come back for some extra questions. So let's give the big Zoom applause there. Thank you very, very much. So where we're going to go now, we have quite a few images, but Chuck Cinnamon. So once again, Chuck, thanks for bringing Danny to our attention and getting me hooked up so we can get him here tonight. And Chuck, I'm going to take back the screen share. Let me get some of this other stuff off. Yvonne, you're doing a great job managing the chat. Thank you very much. Let me go back to my screen share. And Chuck, we're going to jump over to you.
Okay.
As soon as I could get my screen share to work. There we go. And if I did this right, we're all going to be all good. There we go.
All right. Thanks, Phil.
Yep. So just for you guys to know, Chuck's given a presentation before to show his backyard observatory, which is quite extensive. And it's kind of like a neutron star itself. It's very compact and very powerful. So it's some cool stuff.
So, it shouldn't come as any surprise that, the emotion, the passion that Dan's put into his presentation today stirred me to be a volunteer astronomer for him immediately after I heard him speak for an AAVSO seminar, I immediately messaged him and said I would like to be part of his beta team, and thankfully he accepted me to be part of it. What I wanted to share today is just how easy it is to be part of this. It doesn't take a backyard observatory. I mean, I will tell you, I was a little bit concerned, that many of the objects, the extragalactic objects that Dan talked about, are in the 16th, 17th, 18th magnitude range. And I was thinking, how could I possibly, when I normally image things that are 12, 13, maybe 14th magnitude, doing photometry, contribute anything meaningful and important. So what I'm going to share here is just really quick how refit works, how I use it, and the results that I've gotten. So as Dan mentioned, refit gives you recommendations. And when I put my telescope into his system, every day, actually twice a day, I get an email. And that's what you see in the upper left here, which is the top recommendations. And it comes with an attachment on that email, which is the full set of recommendations of objects that are visible from my site for that night, giving you the RA, the deck, predicted magnitude, so I can then plan how long I'm going to need to expose in order to get a meaningful image. And then Dan has set this up now with his team, great team of students, that are working for him, that are working on this website, making it much more user-friendly, where you go accept or reject which targets you would like to go after. So that, then, allows Dan's team to know and expect, what they're going to see results coming back. Dan showed on the bottom right, there's these data brokers that provide the information, through the transient reporting, but it's available to us too through his refit website to actually go look and to use this data both as a finder to make sure you're looking in the right place after you've taken your image. It also shows you the light curve to date. And it also gives these images that Dan showed, which is, the science image, the template, and then the subtracted image, so that you can then kind of compare, what should I be seeing if all goes well. You can go to the next slide. So, once I've picked out my targets, the way my observatory works, I then go build a plan. I collect the images, I do everything that normal astro imagers would do, which is to calibrate those images. What I've done is, because they're so faint and I'm taking 10-minute exposures, I've been stacking them to try to just build up a little more signal to noise. And then what you're seeing in the upper right here is actually a stacked image. And then through his website, I go upload the image as part of the reporting process. And then the last slide here is just to give you samples. I don't have all the postage stamps that Dan showed, but over the course of the last few months, I probably have about maybe 24. And what's really interesting is, these are very far off galaxies in some cases. One of them, I was actually able to figure out what the galaxy was, and it was 540 million light years away. And I clearly saw, one of these, supernovas going off, and it just was very meaningful to me to be part of this. And I want to thank Dan for allowing a volunteer like myself to be part of it. So back to you, Phil.
Thanks. And we're going to adopt and promote, give you full credit for volunteer astronomers. Like Wayne pointed out in the chat, and then I agree, I'm always explaining that you'll see in a moment the quality of the images that come from our group here in light polluted skies. And I always tell people the only reason they're not professionals is they don't get paid for it. So your analogy with the volunteer firefighter is spot on. So thank you very much.
Absolutely.
So now we're going to move to yours and mine and our own organization here's work. Normally I save my own pictures towards the end, but because I was so excited, I implemented my executive privilege and put it up front. So lunar libration, some of you may have seen this on our Google chat area, but it is super cool. And we have we just, thanks to Bob Prokop, our own lunatic, for calling this to our attention when we were out the other night for the impromptu on September 19th. And Chaz, if you're on, I still owe you a report, I know. He pointed out that there was going to be a libration event. And so I grabbed this. So when you look at the picture here on the left, this is the one that's behind me that you also see hanging at Robinson Nature Center and Astronomy Magazine and stuff that I took in 2013. And this is the one I took. And it's interesting, it was almost the exact same day of the month, September 21st. And then this one was on September 19th, just a few days ago. For those of you with critical eyes, this wasn't as full as it was on September 19th of this year, where it was 98.6% full. It was closer to like 95. So that's why some of these features appear to be closer over on this edge here. And also this was done with 130 millimeter telescope. This was done with 105 millimeter. And this was done with over 250 images stacked together and measured. And so I had a lot more detail in all of this than you see here, because I didn't put that much effort into this one to get all that detail out, because that's not what I was trying to capture. But you could see what the moon looked like if you look up right over here, and what you can't see. And now when you look at it right now, you can see all these craters here that were on the far side of the moon on this back in 2013, you get from the same image. And that's because of the libration, which is a wobble in the moon, which happens a lot. It happens, and it's a result of gravity and our position relative to the moon and the angle and everything else like that. And it causes this wobble to occur. And many of you have these moon maps. And if you look at the top edge of this, it's not an outline. What it is showing the libration zone. And what will come visible depending on what that wobble is at whatever point in time. And it was really exciting for me, just as Danny was really excited about, seeing that one pixel light up there. And I got just excited about this. And let me go to the next slide here.
Phil?
Yeah.
Before you go, something that strikes me even more is the relative position of Tycho.
Right. Yes, you can.
That really shows the libration, I think, a lot better because
Right.
of the confusion with the terminators.
Yeah, and that is literally the literal picture of what you pointed out. It's not because of anything that I had done from observing positions. So yeah, so there's a lot. It's so cool when you think about that, moving that planet or moving that moon rather. It's pretty damn cool. My wife doesn't think so much, but I do. So, but here's a closer up view. And like Danny, this was not planned. It was not rehearsed. You could see my research partner down here. Rocky, I've got all my moon maps out and my moon books of all different kinds. And Rocky was helping me with the research to identify these features, because believe it or not, with all these really nice, the Ruckel book and other ones, the new one, the Luna Cognita, when we get the LRO guys to present again, and I think there's one coming up somewhere soon, that we don't get a good shot of the top of the moon from any satellite images. They're all going like this, so it's really tough to identify these particular craters. I mean, when you look at the maps that are out there, everything is published, the high quality pictures. They're like looking at them at extreme edge on, which is why Bob Prokop really likes looking at Pythagoras here normally, because you can't see the bottom. He could see the peak sticking right out. And now, because of the wobble, because of the libration, you could actually see inside this crater, which you could not do before. So pretty cool. And Rocky's a great asset to me because he picks up on things that I don't. So that's my contribution. But here, this one is from Brad.
Yeah, this is the Crescent Nebula in Cygnus. It's a narrow band image with some RGB thrown in for the stars. Some Mission Nebula caused by a Wolf-Rayet star in the center that actually came out kind of purplish in this, which I'm not 100% sure why. On the right-hand side, I inverted and showed the two different channels, because what I find really fascinating is the H alpha filter on top and the O3 filter on the bottom. You see very different topology, if you will. The particularly oxygen is almost looks like soap bubbles. There are very defined edges to the emission cloud that's being lit up. Whereas the hydrogen alpha is almost, you miss those hard edges, but it's all very turbulent looking in the middle. Not quite sure why that is. I've been trying to read up on these, but so that's my contribution.
That's awesome.
Yeah.
And you know what everybody's going to see here is you're going to see throughout the picture today, as usual, that there's going to be a lot of the same objects that have been imaged, but everybody's got their own flavor on it and their twist, and you see different things, and it's really, really cool. So this is one of my this is a great picture, Brad. And now Arjun, this is Arjun's first work, and we're really excited to have you share that with us here at this meeting, Arjun. For everybody, for anybody who's new, Arjun is a seasoned professional, seasoned volunteer at 11 years old, and he's been asking a good number of the questions tonight. And Arjun, you want to just unmute and tell everybody where the telescope was that you used, how you used it real quick, and we'll go to this one and your next picture behind it.
Yeah, okay. So this is the Pegasus cluster located in the constellation Pegasus. I used a 100-second exposure, but like they were divided into different images, one with a 10-second, the second exposure with the 30-second one, and the third with the 60-second exposure. Its magnitude was 6.4, and so far I've been basing all my other pictures off of this one because Mr. Joel's actually been helping me with my pictures. So like I feel like I should go with Mr. Joel's observation best. So anything with a similar magnitude to this, I've been using the same exposure.
And you're not using your telescope in your backyard, right? You're using remote telescopes?
Yeah, I'm still using remote telescopes because honestly, I can only use my telescope on the weekend because like I have to wake up at 7:30 for school. Yeah. No, I really need to mention that.
Yeah. No, excellent, Arjun. And here's two of your other pictures.
Yeah. So the second one is M74, the Phantom Galaxy. So it has a magnitude of 9.2, but surprisingly, I misread it as 7.4 or something. So then I gave it like 110 second exposure, but then it still came out good. So like mistakes can lead to success. So yeah, I'm pretty proud of this image, honestly, because on Wikipedia it said it was the hardest image for amateur astronomers to observe. So it came out pretty good. And then this third one is M41, the Open Galactic Star Cluster. It has a magnitude of 4.5, so I just gave it a 50-second exposure. This actually, I did not intend to take it like this because just today I was reminded that it had a greater, I was not able to fully observe this object using the telescope which I had. So I was just reminded that of today. But all I was mainly targeting for was the two stars in the middle with like the spikes, and I got them. So this image was a success.
Very good. Well, congratulations, Arjun. Excellent. All right, you're a tough act to follow, but we're going to do our best here. Oh, speaking of that, I think this is Wayne here.
Yeah, this is NGC 7331, as you can all read. It's the Deerlick group of galaxies, also in the constellation Pegasus. This is about 7.5 hours of exposures in LRGB.
And you got another one coming. You have another one coming up after.
Sure.
The Case family.
Oh, yeah. So these two shots are the same nebula. One is taken with the our larger 130 millimeter refractor, and the other one is shot with the Red Cat, which some of you are familiar with, the Williams Optics 250 millimeter. So interesting, just two different perspectives of the same nebula. The one on the left was shot at the impromptu. So it's nice to be able to share some of these. The rest of the shots, I think the two that we have left to share were shot on the impromptu night. So huge thanks to Wayne and the team that likes to stay out till 3 or 4 o'clock in the morning taking shots with us. So if you want to go to the next one.
I do want to say this. There's a number of people in the club that are looking at making decisions between Red Cat and similar other telescopes and stuff like that. So pay attention if you guys will. Guys, once again, ladies, guys is a general term for me. That for those kind of questions, actually, somebody's looking for some advice right now in the Google group. If it's going to be long, just kind of get their phone number offline, ask them to send it to you, and give them a call. But please respond to some of those requests because I don't have all the answers. I only look smart because I know people who have all the answers. This is all of you. So excellent. Here you go. There's a.
Yep.
By the way, we're going to see a lot of images today. Hey, somebody's unmuted. If you guys can mute, then I'm talking. Thanks. I don't know who that is.
Thanks, Gerald.
What?
Gerald, can you unmute? Can you mute?
There you go. Okay, I got. There you go. Right. Thank you. There's gonna be lots of pictures you're gonna see of the elephant trunk today. So here we go. Okay.
And there was a request in the chat to go back to 7331.
So you could keep moving. I was just excited to see that somebody had targeted it. I had a science project with the Hubble Space Telescope on that galaxy. So and
Okay.
I put a link there, but just it's fun to see it. Amazing, love it.
Thanks. And then, so these were the two of the other impromptu nights. I think I had about 3.5 hours on Andromeda with a UV IR cut filter only. So we're fortunate enough to be able to shoot on an impromptu night with pretty much a new moon. So I think it turned out pretty good. Andromeda is a tough target for as big as it is. Not overexposing the core, which I may have done. But it's my first time successfully getting a picture I was happy with Andromeda. So I'm glad to share that. And then in the bottom right, M33 Triangulum. This was actually the first target I ever shot back in January earlier this year. And we didn't post the first one that we took, which looked like a blue blob. And I've improved a little bit from my blue blob, and now it looks a little bit more like a galaxy. So yeah, I'm just happy with the stars and the color that came out. And again, thanks to everybody at the impromptu night that gave me tidbits of information throughout the night. Very much appreciated.
Great. Victor.
Yeah, so I also chose this as my target this month. And I also shot narrowband, and I also used a Red Cat 51. And this is my first time doing the Hubble palette, the narrowband imaging, and mostly because I have a one-shot color camera. So I've never really tried to use the narrowband S2 hydrogen and oxygen filters. But what I did recently acquire was some filters that were dual band. So I have one filter that is hydrogen alpha and oxygen 3. And I have another filter that is S2, sulfur 2 and oxygen 3. And by using those two filters, I was able to pull out the hydrogen alpha and sulfur are both red. They're very close to each other in wavelength. So by using these different exposures, I was able to pull out the red and the blue and the green channels and turn the greens and blues into oxygen 3s and to use the two different reds as the hydrogen and sulfur channels. So it's an actual Hubble palette created with a one-shot color camera. Anyways, this is from my deck in Ellicott City, and my wife is a Boilermaker, so maybe I should rename my telescope. Yeah, so this was something like 45 images that were 5 300-second exposures with each of the 2 filters taken a couple of weeks ago.
Excellent. Back to you, Wayne.
Yeah, we already talked about this
Ready.
one.
I got it in twice. I liked it so much. There you go. I thought I put them together. There you go.
So I'd like to, first of all, thank you for separating my image of this from Brad's image because they're very different. This is LRGB, whereas Brad's was at least mostly narrow band. So we're getting a little bit of a different view of the Crescent Nebula. So this is almost 7 hours of exposure time from Alpha Ridge Park with an 8-inch telescope.
Cool. Jamie, I think this is your first moonshots, right? Are you on? Jamie? Yeah, I see Jamie's there. Maybe his mic's not working. Jamie, we don't hear you, but I can see your box. Well, I think so. I believe this was Jamie's first moon pictures here. So both of them. I was going to ask him how he got the red, orange there, but we'll wait to see if he can pop back in. But excellent job, Jamie. Thank you very much.
Phil, I can tell you how he got the orange the night that the moon was at first quarter. There's a lot of smoke out there, and it was orange even as it transited the meridian.
Cool. Thanks, Jim. All righty. I didn't put a name on here. I'm sorry. I forgot who.
It's me, Phil. Can you hear me? It's John.
Yeah, we can hear you, John.
Okay. Well, I just want to give another plug to the Red Cat. All my pictures here were taken with the Red Cat. I think it's just it's a wonderful little telescope and does amazing things. So, so the first one here is a North American Nebula and the Pelican on the right. It's like 4 hours, and I used a dual narrowband filter. It's HA and O3. I was pretty happy with this. Then next slide. I wanted to try something different. So I took the same set of data and I followed a little bit different processing routine, kind of changed up the colors a little bit, sort of a hasty process. My stars, the bright stars are just not as good, but I definitely like the simulated SHO palette that this gives, using the exact same set of data.
So I know how I missed your name. So a request, which I never think about it, so I'm putting everything together, is if you could find a way for everybody when you send them up, to put your name on there. Because what I do is I put the names on. So John, what I was doing, I was putting all yours together. I was going to put it there once and copy and paste it into the other ones, and I forgot to go back. So before I post it have it posted on the website, I'll get your name on the pictures.
Okay, great.
They know. There you go.
This is another. This is the Cocoon Nebula. It's pretty small for the Red Cat, and I really like the. To me, it looks like a fireball going through the stars with the dark nebulas behind it, local dark nebulas, and I was really pretty happy with this. I wasn't expecting much, but it's a really dense region of the sky. You can just see. I think this image had more stars than any other image I've ever processed.
Oh,
and I'm sure there's a supernova in there somewhere.
Just to digress completely for a second, you made me think of something when you were describing this. When we had the public star party, it was about 10 o'clock, 10:30. I don't know if anybody was standing around me, but there was a young girl who turned to her mother and said, "Do we ever see a shooting star or a meteor coming, happening?" Literally within seconds of her asking that question, one of the biggest ones I've ever seen came shooting from west to east, and it covered probably about 40% of the visible sky. And so it wasn't just a flash, and a bunch of us saw it, but it was almost like she called it out on demand. It was, there was a lot of people around to see it when I hear her ask that question. It was a little spooky, but it was cool. There you go, John. I think it's your last one.
Yeah, it's the last one.
I think that girl is going to become a professional astronomer.
There you go.
It's 11:30 at night, and she was just asking. I was like, why? I was ready to fall asleep, asking all these questions in the observatory that were really spot on. she was a real, I think she's got a bright future, that kid.
So yeah, this is my last picture. Like most people, I was pretty clouded out in August. I think I only had one night under the stars in all of August. But this is the elephant's trunk again. Like the others, this is shot with my dual band filter, so it's HA and O3. I did try that processing trick that I did with the North America and hoping to get an equally colorful, vibrant image, but I just I couldn't make it work. I don't know if the composition's different in this picture, but yeah, I was pretty happy with capturing the elephant's trunk with just a 51 millimeter, 250 millimeter focal length scope. So
Cool. I
that's
also
it.
love the way these three stars are just. Yeah. Brad. Back to you, Brad.
All right. Hi there. So yeah, this was the Crescent Nebula. So I guess we got 3 of those tonight. This is through, I have a 130 millimeter refractor that I took this through, and I was using a narrowband filter, a quad band filter, so it passes hydrogen alpha, hydrogen beta, sulfur, and oxygen 3. And this is like, I think 5 hours of 5-minute exposures.
Great.
And that's the bubble nebula, which I really like the way that how round the nebula is in there, because it's kind of like a rare thing, I think, to see something that looks that kind of like perfectly round. That's through the same setup and with the same amount of time, basically.
With some of these crescent images and your bubble nebula, it's amazing the 3D effect that we're getting.
Yeah, it really does look 3D. It's pretty wild. And then this is through my 60 millimeter refractor with the same filter and one-shot color camera. So we got the Pelican Nebula, and then part of the North American Nebula, the Cygnus Wall part of it. So that was a real pain, swapping my whole rig to take pictures through a different camera. So I spent 2 nights doing that.
Cool.
And then so on the right, the North American Nebula, that's through the 60 millimeter again. And then on the left, the elephant's trunk through my 130. Yep.
Jim.
Okay, this is the North American Nebula. It's about 75 minutes through a Red Cat 51 also. And use a Nikon D850 as the camera. No filters, just straight up pointing it with a tracker on the deck from Anne Arundel County.
Cool. Very nice. Thank you. Mr. Connolly.
Good evening, everybody. So I've got a 6-inch Newtonian that I wheel out in my front yard from my garage, and this is the Dumbbell Nebula done with some live stacking. And I'm still kind of new, learning how to image and then process it with my ZWL.
Cool.
And this was the Omega. I took this a little earlier in the month, and I never shot that before, but I kind of like the colors, and it looks pretty good in a zoom background.
Yep.
And this was my Trifid nebula shot that I was able to get after about 15 minutes. Again, live stacking. I'm not sure if folks do that or not, but I thought it turned out pretty good for a short period of time.
Yeah. Now, are you tracking, or are you just doing time exposures, or with your telescope?
Yeah, so it's I don't have any guide scoping on it, so it's just an equatorial mount, and I use Sharp Cap and then let it kind of align the photos when it live stacks.
Got it. Okay. Hey, that was it. So thank you very much, everybody, for all your great images again, and all your contributions, and Chuck for introducing us to Danny. And Danny for coming, and Don Nab, if you're still on, thank you very much. What I'm going to do now is I'm going to officially stop the recording, but keep the call open for anybody who wants to stay on and talk with each other and ask Danny questions or ask each other questions. So with that, call the meeting officially closed. And let me go to the stop recording, and have a good night, everybody.